Okay, so let's start the session. People will keep on joining. First of all, I welcome you all to this 71st session of Praktani Adda. So, this is a monthly affair. We have some distinguished alumni for these sessions who takes us through his career path and some new areas which we all can explore. Today we have from the 2007 batch Debdatta Sinha, and he will be talking about a very trending topic that is of big data and how data is shaping the world around us. So we all know that a lot of activities are happening around artificial intelligence and machine learning with a number of models getting so much attention. So we will see how his work is using data and how the path forward about big data and machine learning will shape the world around us. So for moderating the session, we have Ketan Vatsalya. He is from 2007 batch, and I will hand over the proceedings to him now. So Ketan, please.
Thanks, Satyam. So yeah, as Satyam mentioned, we welcome everyone to the 71st edition or installment of Praktani Adda. I think the previous installments of the series have covered topics ranging from medicine to law enforcement, defense acquisitions, filmmaking, and today it is with great excitement and I have to admit quite a bit of pride that I introduce my classmate, Debdatta Sinha, Dr. Debdatta Sinha, and to talk about data science and its role in the world around us. Uh, I'll do a brief introduction about Debdatta. I won't go too deep into his research. Um, I'm sorry, keep getting interrupted by these notifications of people joining the thing. It's okay.
I will manage it. You can just continue.
All right, great. Thanks, Debdatta. Debdatta and I, were classmates. We both did our 10th and 12th exams, completed our senior secondary education from Vidyapeeth. After that, Debdatta, and Debdatta, some of the details of that I'm going to share, I pulled off LinkedIn last night, so please correct me if I go wrong somewhere. But Debdatta completed, after 12th, he completed his master's in science from IISER Mohali, and he did his PhD, his thesis on. Uh, Sorry, I want to make sure that I get this right. So it's social choice theory and max plus algebra, and maybe he can talk a bit more about it, during the talk. But yeah, and he won the President of India gold medal for that. So, and then he went on to complete his PhD from the University of Maryland, and again focusing on data-driven decision making and logistics, which is also kind of sort of like the underlying theme of his career, and also will be, I think, featured heavily in the talk today. So he's uh, he's worked as a research scientist at Staples, and he's currently employed as a principal research scientist at Oracle, and again focusing on operations research. And at the same time, he also sits on several boards. So on the boards of University of Maryland, University of San Francisco, and on the board of Cheeky Scientists, uh, which is a company that or a platform for basically training PhDs for industrial jobs. So I can think of no better person to talk about the role of data science in the world around us, because not only does he have the theoretical grounding in the data science and the math that's needed for this discipline, but also he has quite a bit of real world experience and in its application in logistics, and this has been sort of like the central theme of his research and his works. So uh, I'll hand over to Debdatta to talk us through, more of his research and his work in as at Oracle and Staples. So before I do that, though, let me break it down basically the structure of the talk today. And thanks, Satyam, for sharing this with me. So basically, the talk will be broken down into two parts. We'll have a 30-minute talk by Debdatta. This is all these are like fuzzy boundaries, though. And then a 15-minute Q&A where we'll take questions from the participants. Uh, that said, Dedato, if you feel like taking questions in the middle of the talk, please, feel free to do that. And yeah, with that, I'll hand it over to Dedato.
Thank you very much, Ketan, for uh, giving your time and also for the kind note. Yeah, so I think clarification questions are fine. If there is anything particularly on the slide that I'm speaking which has to be clarified, please ask that question. But anything related to the general field of data science, optimization, ML, I think those questions are better for the end of the session. Satyam, shall I share my screen and start?
Yes, yes, please.
Okay, thank you. Is it visible in full screen mode?
Yes.
Okay, welcome everyone. I'll get started right away. Yeah, so I did my 10 and 12th from Vidyapeeth 2007 2009. Just to kind of give a brief a connection to Vidyapeeth of who were the Maharajs when we were studying. So when we came in 2002, ours was the first batch that started admission of class 6. Before that, it was class 5 admission for our seniors. So yeah, we did start that trend of class 6 admission. No further admissions of classes to classes 4 and 5. And when we came, the chief warden was Mohan Maharaj, and our secretary Maharaj was Suviran Maharaj, the great Suviran Maharaj. Everyone knows about him. So yeah, and when we and the vice principal was Dhruva Maharaj also. And Ketan, if I say any information incorrectly, do correct me about those things. Yeah, so Dhruva Maharaj was there, uh, and then after we I completed 10th, some of the folks continued to plus two. We got some new joinees in class 11 from outside also. In class 11, as soon as we started class 11, Suviran Maharaj left for being the general secretary at Belur Mutt. And Swami Sarvaganand Maharaj, who is also a very renowned musician or singer, so to say, he became the secretary of the school. Uh, on the plus two side, the chief warden was Vipul Maharaj, who is now the secretary of the whole school, and the principal of the academic block in plus two started was Rajendra Maharaj. So he has left Ramakrishna Mission now, and he has his own ashram near Nashik in Trambakeshwar, Sri Ramakrishna Arogya Sansthan. But he's a very dynamic personality. And after he left, I think even before we completed plus two, he left, and then other Arijit Maharaj actually became he was a brahmachari then. Arijit Maharaj is very close to Vipul Maharaj now. I mean, they manage the secondary section now, I believe. Yeah, so that's the timeline when Ketan and I were studying. We were also the first batch during which the class 8 excursion stopped. So we did not get to go to a class 8 excursion. Our seniors went. Uh, yeah, things happened, things changed. But other than that, it was a very memorable experience, and it really made us strong for the real world. That's what I would like to add. Okay, now going to the actual topic. So I have a few slides about my quick academic and work journey. After that, I really thought what should be the topic because data science is a very broad topic. So I was and this was the most difficult talk for me given the diverse nature of the audience, how to prepare it, what to present. And so what I thought was there were two data science talks preceding my talk. So given that I went through those and I saw what were covered. So I wanted to do something differently or from a different kind of a viewpoint. So there were two ways. Either I could have showed various buzzwords or various domains where optimization ML is applied. Um, but that was already done in few of the earlier talks I'm mentioning, and I have linked to those at the end of the slide. So I thought, okay, let's let's attack the problem from a different viewpoint. So as an outsider who knows about data science but who hasn't maybe worked quite a bit with data science, math, optimization, ML, I thought maybe giving a grounded example would be more impactful. At least after the talk, you would be able to take home something that, okay, this is what I understood, and this is how some very seemingly different fields connect. So that's what I have tried to achieve in the slides. But at the end, during the QA, any general questions also are welcome about the whole field. So data science is just applying any scientific techniques, any mathematical techniques, computer science, statistics to data. Like you want to process data and you want to kind of learn something out of it, or you want to make decisions using that learning. That's the general definition of data science. Now, what techniques we apply, like where those techniques are coming from different fields of studies, as I said, math, computer science, statistics, operations, research. That's where all the research and that's where all the kind of work goes. You develop techniques or you use tools and then you apply it on some data and try to kind of get meaning out of it or try to build better solutions using that. Okay. So this is my very brief journey after Vidyapeeth. So yeah, like everyone, I wrote the IIT exams, and so ICERs are very new institutes. They started in 2007, Indian Institute of Science Education and Research, and they have at this point they have 7 campuses. Back in my time, they had 5 campuses, and the two modes of entry back in the day was either you write the KVPY exam, the Kishore Vaigyanik Prosthan Yojana exam, or you are a ranker in the IIT merit list, and then you get a call from here from the ICERs. After my time, like I think in 2010, 2011, they also started the third stream. In the third stream, if you are one of the board toppers or like across the different boards, CBSE, ICSE, or any state boards, then you don't get a direct admission, but you qualify to write an entrance exam separate for the ICERs, and that's how you get into. So now there are three streams to get into it. It's a 5-year program, BSMS dual degree. The first 2 years you study PCMB. It's a pure science institute or institutes. It's only for sciences. So first 2 years you have to study everything. Even though you didn't have bio in plus two, I didn't have bio in plus two, that's fine. But yeah, you have to study it anyway. You have to learn the science. In third and fourth year, you get to choose your major. I did math as my major. And in the fifth year, you do a master thesis on a topic, which is what I did at ISI Delhi. Then right after my education there, I came to the US for my PhD at the University of Maryland, and there I worked in operations research. Yeah, operations research is applied field where you again pull in techniques from pure math, computer science, statistics, and also you develop new math for that. It's a pure field of study, but it gets tools and theories and knowledge from these other connected fields, and you apply to solve more applied or more business kind of problems. And it can be from various domains. It can be from logistics, supply chain, finance, any field you think there is a decision making problem involved, there is some statistical machine learning problem involved, there is some optimization problem involved. So the math doesn't change, the business problem, the domain knowledge will change, how you interpret the results will change, but the core fundamentals, the theories, the math and computer science, they remain the same. Okay. So and after I completed my PhD, I yeah, directly went into industry research. So I worked at Staples for 2 years. It's one of the largest B2B retailers in the US. I was working there in the last mile optimization problems, middle mile, last mile optimization kind of problems. Then in 2021, I moved to Oracle, where I'm still in the retail supply chain space, and I solve problems like inventory optimization, markdown pricing optimization, forecasting, product recommendations, those kinds of problems. Okay, now moving forward. Okay, so as a PhD, I mean, you are very, like, you have academic lineage because you work with the academic field very closely, and yeah, so like in terms when you get a PhD, it's like they will kind of say, oh, who is your academic sibling, who is your academic father, who is your academic grandfather. There is also a proper database maintained. It's called the Mathematics Genealogy Project, and so it's all the PhDs globally who has completed their thesis in math, applied math, statistics, computer science, anything in the mathematical sciences field. You can actually go back and see 10, 20 generations of previous people. You can literally see your academic tree, where your kind of academic advisors are coming from. And if you see that graph, it's very, everything goes back to Hungary, Germany, because that's where the initial research, like the whole formal education training, degree of PhD, the academic formal setup started there. And it's way back, literally, it's like early 1100s or even before that. And then you can see the kind of connection spread globally. People moved to the US, to Asia. I'm not saying that in India there were no kind of research, and those we have like thousands of years of knowledge. But what I'm saying is the latest version of the formal education, the academic kind of the setup, the PhDs, that was kind of incorporated in Europe, and that spread has now spread globally. So in the previous slide, there was a note, ADOS number 3. So it's actually in the honor of this great mathematician Paul ADOS. So he's the is the he has published the most number of papers in the field of mathematical sciences, even till date, compared to any other researchers in the world. And so in his honor, people have started a kind of number. It's like a graph. So how many distances you are away from Paulidos, and what is the shortest distance from Paulidos in terms of the publications you have, which basically means this person, Daniel Kleitman, directly co-authored with Paulidos. So he has a ADOS number of 1. ADOS has a ADOS number of 0. This is my PhD advisor. He co-authored with Daniel Kleitman. He never wrote a paper with Paul ADOS. So his ADOS number is 2. And I wrote papers with my advisor. So I have a ADOS number of 3. Now, if you imagine, as time passes, um, it's harder to get smaller ADOS numbers, because all these people will no longer be alive. And so the best you can do is maybe collaborate with a ADOS number 3. So at best you can get a ADOS number of 4. But yeah, so that's an interesting kind of thing to observe here. And and uh, and another fun fact. So the average ADOS number of Turing Award winners, Turing is the, like, Nobel Prize in computer science, is 4. And my ADOS number is 3, so I can be very happy about it. Yeah, but it's only for the honor of Paul ADOS, that this thing, the graph distance from how far you are from Paul ADOS in terms of your co-authors in your papers. And this is my academic lineage. George Danzig, Thomas Magnanti, and then my advisor Bruce Gold. And so George Danzig, he is known as the father of linear programming. So linear programming is a very fundamental concept in optimization. And he was the person to develop the first algorithm to solve a linear optimization or a linear programming problem. This programming, the word I'm using is different from a general meaning of computer programming. Linear programming basically is a linear optimization problem, and there are and these are NP hard problems. Some problems I'll give an example. That's what the talk is based about. These are NP hard problems. I'll explain like what is NP hard. These terms might not be readily easily understandable. Yeah, so George Danzig was a father of linear programming. So he was actually at the University of Maryland, from where I did my PhD. He was an undergrad there, and he walked into a class 10 minutes late. And by that time, the professor who was teaching the course, he wrote some problems on the board, and those were actually open problems in statistics. Open problems who at that point no one has ever solved those problems. And when he walked into the class 10 minutes late, he thought it's homework problems. He didn't hear that it's open problems. The next day he came to the class, he actually solved those problems. So such was the brilliance of George Danzig, and he went on to develop so many like new concepts, new ways of solving problems. As I said, linear optimization problems, and that really opened and boomed the field of optimization in a proper way. Yeah. Okay. So this is my like academic lineage in terms of ADOS number and my PhD lineage, and these are some other very well-known academic people both in India and outside India, who I have been like a student to them in terms of I did my master's thesis with them, PhD dissertations with them, research internships with them. Yeah, so I'm very proud of my of the great people from whom I've learned in my career. And people like young crowd, if you're interested to study about math, computer science, optimization, these are the people to search and learn from their work. I mean, this is a very good place to start. What they have done, what what field they're involved in, it's all related to the mathematical sciences, and you'll get so many interesting papers and interesting knowledge to gain from their papers and their websites. Okay, now I'll start with the actual topic. How am I doing with the time? Okay. So let's, as I said, I'll keep my talk very grounded with a very realistic example, and I'll show how a same problem can change its variant by making the problem more complicated, more realistic, and how the same problem pulls in both tools and techniques from optimization and machine learning. How are they even connected, right? They seem so very different. And machine learning is a cool word. Everyone wants to kind of use that or say they know machine learning, and optimization, hardly anyone knows about it, I assume. And we'll cover that. So let's look at a traveling salesman problem. So what is it? So you have a set of cities, like n cities. These are cities, right? Or these are houses in a city, whatever you want to think. I am a salesman. I have to go door to door to sell my product, right? And I have all these houses or customers to cover. What is the shortest route I can take to cover all these cities, right? Because every pair of houses or nodes so this is a graph. You have nodes, and you have edges between the nodes. Like you can build any edges in the nodes. You can go from any city to like any house to the any other house, or any customer to any other customer, or you can think of it as a city, whatever you want to think of it. But I want to kind of travel the shortest path, because all I want to do is cover all the cities, but I better do it in the shortest way. This is a very fundamental optimization problem, and this is computationally a very challenging problem, because if you want to kind of write down all the different solutions possible, for that you will have to take a solution, like this is a solution. You don't know whether it's shortest or not. You swap the order of two nodes. So from this node, if you're able to see my mouse, from this node, let me first visit this one, and then go to this one, and then go to this one. So I just swap the order. And you can do like swaps among the neighbors. You can do swaps like across the neighbors. So maybe you can swap the order of these two. So from here you will go here, follow this path, come here, and then you go here, right? So you can do all sorts of combinations, and exponential number of combinations in generality. And therefore, there is no easy algorithm. In computer science world, we call it polynomial time. There is no polynomial time algorithm which can give you the best solution, or we call it the optimal solution in a reasonable amount of time. Yeah, so it's a very challenging problem. And how we solve this problem, like mathematically, you write a mathematical formulation. Remember, I was talking about linear programming, mathematical programming. This is what a math program is. Basically, you write a mathematical formulation. What are the basic building blocks of a mathematical formulation? Well, you have a decision variable. You have to decide, right? You have to decide from which city I will go to which next city J. So that's my decision variable. So I'm going from this city to this particular city, but I'm not going from this one to this one. So this variable, this ij will be zero, xij will be zero, but this particular xij will be one, because if I choose that as the solution, given a solution, this will be my variables xij. This xij is one and this xij is zero because I'm not directly going from here to here. And then I will have an objective function. So I'm minimizing my total cost. I'm saying if I go from I to j directly, I will count the cost of I to j, and the cost can be just the distance of I to j. And I'll then sum over all the pairs I'm traveling, and in total I have to minimize that. That's the shortest path or distance I'll travel. And there are some constraints. So that's a generic mathematical formulation. You have an objective and you have a set of constraints. What are the constraints doing? The first constraint is saying I can leave a city only once. And the second constraint is saying I can enter a city only once. Basically, I cannot like have multiple paths merging to the city, this city, and multiple paths leaving from the city. Then I'm doing more work. That doesn't make sense, because I just have to visit each house once. That's the task, and so I'm done. So these are the constraints that enforce that. And the last constraint is saying I need one complete tour involving all the nodes. I cannot like cover these cities in a complete cycle, and then I can have a separate cycle covering these cities. No, that's not allowed. I just need one complete cycle across the cities. And this is the constraint that particularly makes this particular traveling salesman problem NP hard problem. This is the polynomial. This is the exponential constraint, because this is saying I have to avoid all combinations of subcycles, all combinations, and there can be exponential number of combinations of subcycles. So that's what makes the optimization problem hard. Anyway, uh, so this is the basic of optimization 101. Now, there are other kinds of optimization. If you're in finance, portfolio optimization, you can pick any field. You have a decision, a minimization, maximization decision making problem, and you have a set of constraints that are very specific to the problem you're solving. And given those constraints, you have to find the optimal solution given those constraints. If you remove those constraints or change those constraints, the optimal solution will change. Okay. Now, so I gave an example of optimization problem. Now let's go through these topics. I mean, just some keywords. Now, what techniques and tools do I need from other fields to solve that particular traveling salesman problem? Well, I need to have knowledge of graph theory. Spoke about nodes, edges. Graph theory is a field in pure and applied math. I need to know combinatorics. Computational complexity is what I was talking about. That the problem is NP hard, polynomial, non-polynomial, all those things. Mathematical programming is the mathematical formulation I showed. Then optimal algorithm. So when I'm solving that problem, if I can come up with an algorithm that is guaranteed to give an optimal solution, I know that I can prove that that solution is actually the best solution, I cannot do better, then that algorithm is an optimal algorithm. There are approximation algorithms when problems are very hard to solve. As I said, that's it's a very hard problem to solve computationally. So maybe I can come up with an algorithm and I can prove that my algorithm is 5% away from optimality. I can prove that. Then those algorithms are called approximation algorithms. Then there are heuristics. In most cases, for hard optimization problems, I do not have an optimal algorithm. Also, I cannot prove that the algorithm I have is at least 5% away from the optimality or from the best solution. If I cannot do that, then I just have a general way of solving the problem. It gives me a good solution, but I don't know how good the solution is for all scale of problems. Like I can have a traveling salesman problem on 5 cities, 10 cities, 100 cities, thousands of cities. I don't know if the algorithm I have is doing good on 5 cities, but when I have hundreds of cities to solve, there are so many combinations I have to try out. So I don't have a mathematical guarantee that, okay, my algorithm is 5% away from optimality or 10% away. If I don't have that guarantee, then it's basically a general algorithm which is trying to solve a problem in a good way, and those algorithms are called heuristics. So typically, optimal algorithms, approximation algorithms can be a little general nature. Basically, what is this? I mean, people who are interested, this is a convex set. These constraints is giving you a convex set. In a very general sense, you can think of a Euclidean plane, x-axis, y-axis, and just draw a line x plus y equal to 1, right? It will just cut the plane like this. This is y-axis, x-axis, and this. So we get a triangle, right? So that's a convex set. Yeah, Soumya, if you can just mute yourself. Okay. So yeah, you get a convex set. Now you can think of convex sets, more very complicated convex sets in higher dimensional spaces, right? This is a very higher dimensional space, not a two-dimensional space. Um, yeah. So basically, it's a convex set, and the optimal algorithms are just solving math. So you have a business problem. From the business problem, you wrote a mathematical formulation, and the mathematical formulation gives you a very complicated convex set. It also has a function over the convex set, and then you're finding minimas or maximas over it. So now it has nothing to do with the problem. It's pure math, computer science kind of techniques, and those algorithms are actually optimal algorithms, and they're disconnected from the actual problem. But heuristics are more grounded, because if you are not able to solve such a problem from a purist approach, like using pure math techniques, pure computer science techniques, and therefore you don't have an optimal or an approximation algorithm, then you fall back to heuristics. And heuristics are actually more variable problem to problem if the problem like based on the business use case. To give an example, I can have a portfolio optimization problem, and I can still write down a formulation for the portfolio optimization problem, and I will still get a convex set, and I will still have a function to minimize, maximize. So the optimal algorithm might look very same for a traveling salesman and a portfolio optimization problem. However, the heuristics will be very different. The heuristics will be grounded on the problem. So I will how does the heuristic look like? Oh, I'll start with a random solution. This is a particular path to travel all the cities. Can I do better? Can I like do some swaps? I was telling earlier that can I kind of swap the order of these two nodes and see if my solution is better or not, right? So this is very specific to the problem. That's a heuristic. In portfolio optimization, you will start with some allocation of your principal to various stocks, and then maybe you will have to shuffle around some investments to see whether you're getting a better return or not. So the heuristics are very problem specific. But yeah, if you want to learn the field of optimization, you have to be well versed in all these mathematical and computer science fields. Now, machine learning, very, very cool buzzword everyone wants to know. But again, let's focus on the fundamentals. What does a traveling salesman problem have to do with machine learning? Uh, they are very different or looks very different. Well, I can solve a traveling salesman problem using a very basic machine learning tool, linear regression. You can't be simpler than that, right? How can I solve that? Well, I can have data from thousands of cities, right? I can have Delhi, Bombay, Chennai, Bangalore, Boston, Washington, D.C., New York, Paris, London. I have data sets like streets or yeah, and within each city, I have houses, people, customers, and if I get the traveling salesman the optimal route in each of those cities, now I have a data set. How does my data set look? City A, optimal route length 100. City B, optimal route length 110. City C, optimal route length 90, right? You have all these, it's a data set now. And for each city, you can build these independent variables. I mean, in machine learning, you will call it features. In statistics, you will call it covariates. In regression, you will call it independent variables. Whatever you can. For every city, you know how many houses you have to visit. What is the area of the smallest rectangle that covers all the cities? Minimum distance across all pairs of nodes. Maximum distance across all pairs of nodes. Variance of distance across all pairs of nodes, and then some other statistically developed kind of features, right? So for every graph, a city it's a graph, right? At the end, it's a graph. For every graph, you can find the values of these independent variables, and and you have this data set that okay, you have the independent variables, you have the values of the dependent variable. The dependent variable here is the optimal tool length, right? That's the problem we're solving. It's the traveling salesman problem. And traveling salesman problem is also like the basic version of vehicle routing problem, right? You get deliveries at your home, Amazon delivery, Blinkit delivery, all those are vehicle routing problems, which is a general version of traveling salesman. Anyway, so now you have this data set. You can do a linear regression on that using the independent variables, trying to predict your dependent variable. Now, suppose I give you a new city, say Shanghai, and I ask you to, like, there are millions of customers there, or millions of houses I have to visit to kind of solve my traveling salesman problem and find the optimal route. But suppose I am not well versed in optimization. I don't know how to solve optimization problem. I don't know what heuristics are, but I know linear regression. If I have this data set, I can build a linear regression model. And when I have a new data point to predict a new city, say Shanghai, you can calculate all these independent variables of the city. These are known. You can calculate these values. And using your linear regression model, you can predict the optimal tool length. Obviously, there will be errors. A linear regression model has errors. But that's how like you can even solve an optimization problem which has no connection to machine learning using a machine learning algorithm. So that's where data plays a role. So I moved from, so I'm still solving the same problem, but using a very different tool to solve a same problem based on various things to, like, if I have the right skill set to solve it one way versus the other. Do I have to solve it in a very fast way? Optimization can take time. Then maybe I'll go use the linear regression way, right? So this is just a connection of how like optimization and linear regressions are like machine learning in general is connected. And that's true for any problem. You pick a problem. If it's a decision making problem, that means there is some optimization there. And on top of it, you can do some, yeah, you can solve it in a very different way using machine learning tools. Now, if you want to learn machine learning, these are the things you have to kind of get used to: probability theory, statistical algorithms, hypothesis testing, supervised and unsupervised learning, reinforcement learning, neural networks. Now, like, also, like, I would want to ask the question: what do these algorithms have fundamentally common to optimization? Now, forget about the example I gave you. So I picked an example, I showed two different ways to solve the same problem. But fundamentally, if I'm doing reinforcement learning, supervised learning, suppose linear regression, if I just kind of focus on linear regression, how is it connected to optimization? Well, every machine learning algorithm has a loss function. You are minimizing some loss, you are minimizing some error, and that itself is an optimization problem, and we don't realize that. We think, oh, machine learning, it's just some model fitting, something, some clustering, whatever. Everywhere you're minimizing, maximizing some errors, some scores, and that itself is a optimization problem. So machine learning is fundamentally dependent on optimization. Machine learning cannot thrive without optimization. Okay. Now, I want to just carry forward for the next 5 or so minutes and build on this same traveling salesman problem and make it little more interesting. And rather than kind of uh, 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 this far connection between, okay, take a traveling salesman problem and solve it in two ways, I will make this problem realistic enough so that you will actually need both optimization and machine learning directly to solve the problem. So I'll make the problem more realistic. So suppose this is a street network. These are the green dots are houses. And I am a utility company. I have to read the utility meters of electricity, water, right? So every month I have to do the meter reading to bill my customers. So if I'm just doing it manually, I will actually go through all the streets. I will walk through all the streets or drive and get down manually and read the meters, right? But there is also the RFID technology, radio frequency identification technology, and that says, well, you don't have to travel all the streets. You can be close enough. If you're within a certain distance, you will read the signal automatically. That's possible, and therefore you are not traveling this street anymore. You are just traveling this street, and this meter is still within that the radius of the distance. And so even by kind of driving through this, you are able to read all the meters. So this was a traveling salesman problem. This is a close enough traveling salesman problem. You don't have to visit each customer. You have to be close enough to each customer. So mathematically, this problem is even harder than the traveling salesman problem. I will not go into the details why, but that's what computer science and math tells us. Okay, but this is a deterministic problem. I know that if I am within the desired distance from a meter, from a RFID transmitter, I will read my data. Okay, now let's make it more realistic. What happens is this is a real world data from a street network. So these are the different meters, and this is the path that the meter reading driver drove through. And these are the street segments, the route of the vehicle. The blue dots are the data that was read by the RFID driver. So those data was captured. The yellow dots was missed; those were not captured. So you can see even in such a vicinity of the vehicle route, there it's so much of like uncertain or stochastic, I would say, right? Some meters are blue, some meters are yellow. So I can't say for sure that if I drive through here, I will cover all those meters. And also you can see a meter very far away was also captured. So it's a stochastic problem now. So it's no longer a deterministic close enough traveling salesman problem. It's a stochastic close enough traveling salesman problem. So yeah, so just to kind of quickly say, so I can write a math again. It's optimization problem. I can write a math programming formulation to solve it. So these are all my meters. These are all my street networks, the edges between the
मच्छर है
nodes in
यहाँ
the
पर
graphs.
और इसमें मच्छर है
And yeah,
कोई
and this is the cost, right? This is the cost, like the distance to travel. And then this is the service level. So for example, I want at least 90% guarantee that I will read these meters if I drive through here. That likelihood, the service level, right? I want to have a 90 or 95% guarantee. That's the LI here. and then xj is the decision variable that you have to decide whether to drive through this street or not. At the end, right, you have to choose whether you want to drive through this street or not, right? Because it's a close enough traveling salesman. You don't need to drive through all the streets. The meters have a distance, but unfortunately, there is no guarantee. It's a stochastic problem. From real data, we can see, right? So yeah. So then you're deciding of which streets to cover. Even if you don't understand that, that's okay. I have a different fundamental message from this slide, and this is the probability that from street I, meter j will be covered. That's the probability. Now, this problem is no longer a deterministic optimization problem because it has a probability term inside. And unless I estimate the probability separately, I cannot solve this problem because that's an input parameter to my optimization problem. Which is why it's no longer it's a stochastic optimization problem. My decision variable is x. I'm just deciding, all I'm deciding is whether to drive through a particular street or not. But Pij is a probability, and that's the input to the optimization problem. And before I go, how can you kind of estimate the Pijs? I'll just say on the right hand side is a formulation of the deterministic close enough traveling salesman problem. Because in the deterministic world, I know that if I am within X distance or some distance of a meter, I'm guaranteed to read the data. That's what the deterministic version is. So this is basically saying Aij is either 1 or 0. So if my meter I to street segment J, yeah, Ketan.
Sorry to interrupt you, but we have quick time check. We have like about 12 minutes left, and we want to save some time for Q&A as well. So yeah, please carry on.
Okay, I'll just wrap up in the next 1 minute. Yeah. Okay. So we, we can see, right? I mean, so this was a deterministic formulation. There is no probabilities involved. I know for sure whether I will be reading the meter or not if I'm within the X distance, and I just have to choose what street segments I have to do. Now, I have to estimate the probability. So now you can actually go into statistics, regression, Bayesian statistics. I will not go into like the details of that to estimate your probabilities in very advanced techniques. And that probabilities become an input to the optimization problem. So initially I showed in a disconnected way, you take a deterministic traveling salesman problem and you solve it using optimization and machine learning, say linear regression. And then I made the problem realistic. And what I'm saying is, even fundamentally itself, these two fields are very connected. You're solving a decision making problem, and once you have real data involved, you have stochasticity involved. The problem is no longer deterministic. So you have to deal with data and machine learning to estimate certain parameters that goes back and helps you solve your optimization problem. That's all. I think I will keep my slide shared. Yeah. Okay. Yeah, the floor is open for any questions. Yeah.
Yep. Thanks, Debdatta. Thanks for the talk. It was really, riveting. And thankfully, I mean, for sure, I, took a lot away from it. So let's open up the floor. Bear with me. I have some trouble switching to, like the gallery view. But yeah, let's go ahead and please raise our hands or just like, shout out your question. All's good. Anyone?
Yeah, so I have one query. So regarding these traditional ways of how machines learn, so can you just explain why this new thing that so we read about it somewhere that the models that China is developing, it is taking a better or more fast forward way to optimization than what models in the US like ChatGPT had been deploying, which required much more processing usage. Uh, so how do optimization solving differ across models?
Uh, it's a very timely question, given all the noise about DeepSeek versus ChatGPT or other kinds of models, Gemini. Okay, so first I'll fit the question in the context of what I spoke. Uh, so in one of my slides where I was listing all the methods for machine learning, I spoke about, like I noted reinforcement learning and neural networks. So all these large language models that we deal with, either chat gpt or any other like chat interface you are doing, those are some version of transformers. And transformers is a kind of a neural network architecture. And we have to understand that fundamentally those problems are not good at solving logic or mathematical problems. Like people are doing research every day, and those problems are kind of getting changed, like how the architecture is designed. Satyam, maybe you can just mute yourself. There's some background. Yeah. So fundamentally, like a lot of research is happening how to change the training architecture, both the architecture and the training method of those problems to make it better in solving math. But those are basically just predicting the next token in the sequence. So you feed it a kind of a set of sequences, and it produces a set of sequence. Ketan, yeah. But so Satyam, I have to answer complete the answer. Yeah.
Oh, no, no, please finish your answer. I had kind of like a
Yeah.
follow-up to
Okay.
Satyam's question.
Yeah. Okay. But okay. So what these DeepSeek people did was they did one thing very smart. In computer science, there is a IEEE kind of a standard that says all mathematical operations have to be 32-bit. We call it the floating point operations. They said, the DeepSeek team said, why do we need that much of accuracy in the decimal? If the answer is 24.2, I don't really need to report 24.21576 up to 32 decimals, right? So they are doing the operations in 8-bit, and that saves huge amount of storage and computational power, because your model becomes a lot simpler just by that assumption that you're fine to make those calculation approximations, but you solve a lot. And the second thing is they're using reinforcement learning a lot. So what they did was they built computer programs, and they actually competed one computer program versus the other. So reinforcement learning is a field at the intersection of optimization and machine learning. And the way it works is you take any machine learning algorithm, you make a decision based on that, but then you get a feedback from the algorithm itself that whether the decision the algorithm made, given the data it's seeing, right? So the algorithm sees some real world data, it makes some decision. Now it gets a feedback within the algorithm itself that was my decision good or not, because in the next state when I get new data, I can decide whether my decision from the previous time period was good or not. And that's fundamentally reinforcement learning. So what the DeepSeek people did was they made their computer programs smarter in solving mathematical problems, not just token in token out like a typical large language model. And the way they did was actually using reinforcement learning by kind of developing these computer programs which were fighting against each other and improving overall. And the other thing I mentioned was reducing the decimal points in their calculations. Um, Satyam, did that answer your question?
Yes, yes. So, just one follow-up related question to it. Uh, so we have these two business models that current model developers are. So one is this: they would open their models for everybody to use. Somebody like ChatGPT has some bits of it kept within paywalls. So how do these models ultimately monetize themselves if it's made freely available to everybody?
This is a very old saying in Silicon Valley, probably before we were born. If you're not paying for it, you are you are
Yeah, the
the
product.
money,
Yes,
right? You
yes.
are the so so see, for example, Facebook Llama, right? Facebook and Ketan is working at Meta. So Facebook Llama models are one of the best open source models. DeepSeek came to the picture now. And the reason they have made it open source is because so that when you are querying those models, they are also learning. And there's so much of research in Facebook. So I spoke about graphs today. In Facebook, it's all about graphs and relations, right? So you are a node. You are basically a node in the graph, and everyone who is in your friend list is your direct connection, is a direct link to the graph. And so much of mathematical computer science research are happening. And yeah, so Facebook, Meta, the FAIR lab, they call it the Facebook AI research lab. Their policy has been to keep things open source from many years, and this and such kind of other tech companies also do that. And this actually helps the research field grow. And also these companies are getting like tons of data from how the user is interacting with that, and that is actually giving them ideas to kind of build new products to engage us more in the e-world, or the social media world.
Okay.
I was going to ask my follow-up, but I think we have discussed LLMs at length. Let's take Sanjeev's question next. Sanjeev? Sanjeev, you're muted. Sorry.
Yeah, nice presentation, but quite overwhelming for my kind of age. My question is, for those people who are technologically challenged, I mean, the elderly in the age of technology, I see senior citizens and elderly struggling with the mobile phones, smartphones. I see the same kind of problem in case of data science, AI also. So for those who are going to be the users, not the creators of technology, what is your advice to be able to at least manage well and not get cheated or sidelined or swept away?
Dada, this is a very difficult question to answer, but I will still share my thoughts. And the reason it is difficult is it is it is always hard to difficult to place yourself in other shoes and answer from their perspective, which is basically this question is for me. So the one suggestion I would have is, as a user, even though it's like I go to a market and I buy a food product. These days there are so many adulterations in the food, even though I don't really understand the chemistry or the biology of it. But I, as a consumer, I have to at least understand what the label is saying. Okay, it has this much of sodium, this much of that. At least what is written on the label, I have to make that effort to consume that information to make an informed decision whether this food product is good for me or not. On the very same lines, if I'm a consumer of technology, I think it is always very helpful to read some like overview kind of articles. There are so many articles today in Medium, in there's so many all these websites, or even YouTube, experts are sharing their views. And most of those articles, or some of those articles, are actually tuned for the general audience, because there's so many buzzwords floating around, and things are evolving so fast. It's easy to get lost, or not know what to do. So so therefore it starts to inform yourself by at least on a high level. Okay, what is this product fundamentally, and what is this product supposed to do? And therefore I can make an informed decision whether it serves my purpose or not. I think it's very important for everyone to do this much of research to get the maximum benefit of out from all these technologies available.
Okay, thank you. Thanks a lot.
Thanks, Ajita. Thanks for the question. We have, we can, I think, stretch for a couple more minutes if anybody has a question.
Just regarding this privacy issue that we are debating in media currently. So recently in India, the finance ministry actually issued an advisory for all the employees that you should not be using ChatGPT and others for processing official documents. So how realistic are the concerns? Like if you, because is it possible that somebody who is processing through ChatGPT, that the team backend can get access to those documents? Like, does it happen that is it possible for them to look after every query that a user posts to their their platform?
Yes, very very fair question. And not just ChatGPT, right? You go and buy something from Amazon. Your data, your address, your payment details, your credit card, everything is in the database. Who has access to the data within the company? That's a different question. there are IT breaches where data gets stolen. So every data is there in some database of some company. So it's a very, very valid concern. And therefore, you are like, if the company does not allow you, you should not use all these large language models to upload any sensitive documentation. Once you upload, it's gone, unless the company has a special contract with ChatGPT or any such services, and they are deploying a kind of deploying just a version for your company. And then it's a contract between the chat gpt and your company, that the data that your company employees are using in this version of the model, which is only specific to your company, will not go to the public database, like the bigger database. So all those things are taken care by the IT people when they're deploying such company specific models, just to say in the simplest way.
Right.
Okay,
I
thank
see
you.
no other hands. I'll ask, sorry, Satyam, go ahead.
No. I think it was answered. My query was answered.
Okay. So I see no further hands. So I'll ask like one, broader question just to kind of wrap it up. Have we, as we reached a point in this whole machine learning saga where the word has kind of lost all meaning and we should probably abandon it or something, something else or something more specific? What do you think? Does machine learning mean anything anymore?
Does machine learning mean?
Like, is the word too big to mean, like, has it become too broad now to because it's being used everywhere basically?
Definitely. And so like, if I ask someone what is artificial intelligence, they don't know. It's hard to define what is machine learning, how are they different with AI. I mean, I think the problem goes to the marketing and sales domains, because they have to sell product. If my competitor is using those buzzwords and the customer, not having the technical background, is falling for the trap, I, as a competitor, I have no option than not to use those buzzwords. So things have really gotten kind of a little crazy at this point. Yeah, being someone who is fundamentally trained in these fields of math, CS, optimization, OR, ML, statistics. Yeah, these things really annoy even personally me, that things are taken out of context. Like these days, even the term AI has changed its meaning. Today, AI is just generative AI. Like
Yeah.
if I'm talking to a salesperson, a consultant, a customer, and they say, "Oh, AI can do this." Oh, okay, hold on. What do you mean by AI? You actually mean ChatGPT. So over time and very fast, the general usage of these terms are changing too fast, and that's not good. That's not good. It creates a lot of confusions, and people assume a lot of things, which is why I said to one of the Sanjeevs that everyone has to do their basic level of reading of this tech world. Otherwise, it's very easy to lose track and get lost.
Great. Thanks, Debdatta. And you basically echo my sentiments as well. So, and thank you for a very, in-depth and relatable session, at least for me it was, and I got a lot from it, and I'm sure everybody else did as well. So I'll hand it over to Satyam to take us home, and yeah, take it away, Satyam.
Yes. I think very rightly put that. It was a very informative session for all of us who attended it, and it is such a trending topic and often misused. A lot of things currently, but uh, we- to listen to somebody who has learned it both from an academic point of view, and now as a practitioner, I think it was an enriching experience for all of us. Thank you, Devdatta, for taking your time and sharing your wisdom with all of us, and also thank you to Ketan for taking your time. And with it, we can wrap up today's session. And uh, if anybody wants to stay for some informal chat, then maybe we can stop the recording and maybe stay for 5 more minutes.